Welcome to lesson 1.4 and 1.5. We're going to start with section 1.4 on functions. Okay, so important terms that you need to know: independent and dependent variables. Okay, the independent variable is x. That's what we would plug into our function. The y value is dependent, right? It depends upon x. The domain of the function, if you remember, that's your x values. Okay, or your inputs, where the range would be the y values, or the outputs of the function. For function notation, most commonly we use f of x, right? It could be p of x, q of x. The whole point of function notation is to give the function a name, right? So we can refer to it by its name. We don't have to state all of the terms of the function. If you're asked to determine whether if an equation represents a function, there's two ways you can go about that. You could look at the graph, and if you know what the graph of this looks like, you could use the vertical line test, okay, to determine whether if it's going to pass or fail the test based upon does that vertical line go through two or more points. This is the graph of a circle, right? So it's going to fail. It would fail the test, meaning it's not a function. Algebraically, what we do is we solve for y. So I'd have y squared is equal to, excuse me, 8 minus x squared. And then taking the root, the key thing that I need to remember here is that when I take the root, I have to bring in the plus or minus. So it's actually plus or minus the square root of 8 minus x squared. That plus or minus gives me two different values for y, and that's what makes it fail. So it's not a function. We need to have one x for every y in order, I'm sorry, one y for every x in order for it to be a function. Evaluating functions. Okay, so you should be very familiar with this notation. So I'd like you to find each of these, given f of x is equal to 10 minus 3x squared, find f of 2, f of negative 4, f of x plus h. So pause the video, go ahead and give each of these a try, and then when you come back, I'll show you the answers. Okay, let's see how you did. For f of 2, hopefully you got negative 2. For f of 4, hopefully you got negative 38. And for f of x plus h, hopefully you got all of these terms. Piecewise functions. You should have seen these in Algebra 2, right? They're created by two or more equations over a specified domain. So the first function is 3x minus 4, and the specified domain is that that has to be where x is less than or equal to 0. The second function, 3x plus 1, is where x is greater than or equal to 0. So notice there's no overlapping here because we have an inclusive symbol and a non-inclusive symbol. So for these, you want to make sure that you're using the correct equation, okay, based upon the domain. So if you're finding f of negative 2, you'd want to go to the function where it's valid for x less than 0, which would be 3x minus 4. So go ahead and give these three a try. Pause the video and then come back. Okay, let's see how you did on these. So hopefully you got negative 10 for f of negative 2. For f of 0, you should be plugging into the second function. And f of 2, hopefully you got 7. The difference quotient. This is one of the most important things that we cover in chapter 1. This is something that you will use in your calculus course next year. So for right now, what you need to know is how to calculate a difference quotient. So I'm going to tell you where the formula comes from. We have 2 points here on the graph, which I've labeled as x, f of x, and x plus h. Okay, this value, this x value, is h more than this one. So it's x plus h, f of x plus h. And what we're going to do to calculate the difference quotient is calculate the slope between these points. So if I start with f of x plus h, and I subtract the y value of the other point, that's minus f of x, and then that's all over this x value, x plus h, minus x. So we can just do a little bit of simplifying there, and we get f of x plus h minus f of x over h. So again, this is a very important formula. This is what we use to calculate the difference quotient. And we can talk more about what that is in class. For now, it's just important that you know how to calculate it. So you're asked to find the difference quotient for each of these functions. So I'm going to start with this one. So again, I'm going to write it out here, f of x plus h minus f of x all over h. So this first part, just like the previous example, you're plugging x plus h into each x in the equation or in the function. So I'm going to start with x plus h squared minus 2 times x plus h plus 7, and it's all of that over h. So when I square this, I get x squared plus 2xh plus h squared minus 2x minus 2h plus 7. Ooh, I didn't finish this. Up here, we're subtracting the original function. This part here, this is just the f of x plus h. Now we need to do minus. I'm going to put parentheses so that I remember to distribute the rest of the function. Okay, where the original function is being subtracted from the f of x plus h. So this expansion is again just this first part here, and now I'm going to distribute this negative. So it's minus x squared plus 2x minus 7. Now a lot of terms are going to drop out. Let's see what we've got here. So we have x squared minus x squared. We have minus 2x plus 2x plus 7 minus 7. And again, all of this was over h. Now, if you notice, all the terms that remain, they all have an h. So we can reduce all three terms by h, and we end up with 2x plus h minus 2. Now, here's an important thing to remember. We started with h in the denominator, right? The domain of this is implied, right? We know that h cannot equal 0. When we simplify and we lose that h from the denominator, we need to make sure that the domain of this simplification is the same as the original prior to simplifying. So since I've lost the fact that h cannot equal 0, I have to state it. So for most of your difference quotient problems, you're going to be stating that x cannot equal 0. Keep that in mind. Okay, what I'd like you to do is try this problem, f of x equal to x cubed plus 2x. Go ahead and write out the difference quotient for it, and then I'll show you the solution. So pause the video again, and then come back when you're done. Okay, let's see how you did with the next one. Here we go. So you're plugging in x plus h into both x's, and then subtracting the original function. So that gives us this line. When we expand everything, hopefully you know the shortcut. Remember from Pascal's triangle, the coefficients are 1, 3, 3, 1. Okay, you want to get used to these shortcuts if you're not using them. It's a big time saver. And we'll go over that in class remind me to do that. Okay, so we end up with this line after all of the expansion. We have terms again that drop out, the x cubed and the 2x. All of the terms that remain have an h in them, so we can reduce everything by h. And again, since we reduced that h from the denominator, we have to say that h cannot equal 0. We have one more example for you to try. Go ahead and give this one a try. You're going to end up with a complex fraction, so make sure you simplify that. When you're done, pause the video now, and when you're done, come back and I'll show you the solution. Okay, let's see how you did. Okay, so you can follow through the work. If you need to, pause the video again, but if you came up with -21 in the numerator, then most likely you have the correct answer. Check the denominator, and again, make sure that you wrote that h cannot equal 0. Okay, on to section 1.5, analyzing graphs of functions. So given this graph that we have here, we're going to state the domain, the range, and we're going to find out what f of 2 is equal to. So for domain and range, remember we're using interval notation. For domain, we're looking from left to right. What x values does the graph cover? So at this point here, this is our starting point, right? The point furthest to the left. The x value is -1. It's a filled-in circle, so we're including it, so we use the cornered bracket. This is where the graph ends. This is the furthest point to the right. The x value there is 5. So the domain goes from -1 to 5, but we're not including the 5, so we use a parenthesis. For the range, we're looking at the y value, so we want that minimum y value up to the maximum. Our minimum y value is -3, and we're including it. The maximum y value is a +3, and we're also including that one. So the range is from -3 to 3. For f of 2, normally you're probably more used to plugging this into an equation and evaluating. If we have a graph, this is really asking you what is the function value, which is the y value, when x is equal to 2. So if we go to where x is equal to 2, we're looking at this point here, and when x is 2, y is -3. Remember the vertical line test, you can use that again to determine whether if this is a function or not. So if anywhere you can draw a vertical line that goes through 2 or more points, the graph fails the test and it's not a function. The zeros of a function. The zeros are where the graph crosses the x-axis. So we have a 0 at x equal to 1, okay, or 1 comma 0. And we have a 0 at x equal to 4, or 4 comma 0. Increasing, decreasing, and constant functions. Okay, the function is increasing if this means as x approaches infinity, meaning as x goes to the right, as our x values increase, y goes to infinity. So y is also increasing. So we go from left to right, and we look at what is happening with the y values. If as we go from left to right, y is increasing, it's an increasing function. And then that can just happen over an interval as well. That's what we're going to be talking about, is intervals of where a function is increasing, decreasing, or constant. It can also be continuously increasing. For instance, if you have an exponential graph that looks something like this, then all along the graph it's increasing. For decreasing, this means that as x approaches infinity, or as x gets larger, y is getting smaller, right, or decreasing. It's approaching negative infinity. So this is the type of notation that we often use. For constant, as x approaches infinity, y is equal to a. So this means as x is getting larger, y is just always equal to some constant that we're calling a. So a couple of things to keep in mind. We always describe these intervals by x values, and we always use parentheses around these intervals. We're not including those endpoints. It's what's happening over an interval. So it's not like domain and range where we have to decide whether we're going to include the values or not. Relative maximum and minimum. They're also called a local max or min. You'll probably see this in your calculus course next year. These are the points where the graph changes from increasing to decreasing, or from decreasing to increasing. And they're also called turning points. You've probably heard that name before. So what I'm going to do here is write out the intervals of increasing, decreasing, or constant. So if we look from left to right, initially as x is getting larger, the y values are getting larger. So it's increasing from negative infinity, because this graph should have little arrows on the end. It's this function with no restrictions, so this does keep on going. Okay, so from negative infinity all the way to, again, we're looking at x values, -1, the graph is increasing. After that, it's decreasing, right? Because as x is still getting larger, so we go from left to right, but y is decreasing. We're getting smaller. So that's happening from -1 to 1. As we continue on from 1, the graph is going back to increasing, because again, as x is getting larger, as we go to the right, the y values are getting larger. So it's increasing also from +1 to infinity. There's nowhere along this graph where it's constant. Okay, next is slope as a rate of change. So for a nonlinear graph whose slope changes at each point, the average rate of change between any 2 points, and these are the points, x sub 1, f of x sub 1, x sub 2, f of x sub 2. If we plug that into our slope formula, we end up with f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. Okay, so that gives us the slope through those 2 points. And this again should be something that should be reviewed from Algebra 2 from last year. So calculate the average rate of change. Here's your function, f of x equal to x squared minus 2x, from x sub 1 equal to -1 and x sub 2 equal to 3. So try both A and B and this problem using the formula from the previous page. When you're done, come back and we'll compare solutions. Okay, let's see how you did. So hopefully you got 0 for the first one, -1 for B, and 20.06 feet per second. Even and odd functions. Okay, a function, remember, is even if for each x in the domain of f, f of -x is equal to f of x. It's odd if f of -x is equal to the opposite of f of x. So I'm going to go through an example with you of how to determine whether a function is odd, even, or neither. And again, this should also be reviewed, but I'm sure some of you might need a refresher. So what we're basically going to do is plug -x into the function. You do not want to just use a value here, because if I say, well, I'm going to calculate what's f of -1, that really only tells me about f of -1. Right? We want to generalize, so we're using f of -x. So if I plug -x into both terms, when I square that, I'm back to a positive x squared. Raising to the 4th also makes this positive, so I have minus x to the 4th. So when I compare, this is exactly the same as the original function. So when f of -x equals f of x, that means that f of x is even. For g of x, if I calculate g of negative x, I have negative x to the third power. That makes this negative 2x cubed plus 1. So if I compare this, I have opposites here, but I have the same sign here. So I don't have f of x, or g of x. I don't have the original function, and I don't have the opposite of g of x. Those are my two choices, that either I get the same function or the opposite of the function, meaning every sign is opposite. So that means that g of x is neither. So we have even functions, odd functions, and sometimes they're neither. So go ahead and try the next four, okay, h of x, j of x, k of x, p of x. Pause the video, and when you're done, come back. Okay, so here's all of the solutions. Hopefully you found that h of x is odd, j of x is even, k of x is a neither, and p of x is odd. Okay, these are problems that are also important. This is a technique that you'll use in calculus. For now, you just want to learn how to come up with the height function. Okay, so you have to picture a rectangle, very, very small rectangle within this space. Okay, it's bounded by this curve and this horizontal line. So when we're asked to calculate the height of the rectangle, which is going in the vertical direction, think of it this way: if you were calculating the height between two horizontal lines, you wouldn't think twice about it, right? If I say you have the line, hang on a second. If I said this is the line y is equal to 3, and this is the line y is equal to -2. If I asked you for the height of a rectangle between these two lines, you would tell me the height is 5, right? And you got that by doing 3 minus -2. We're doing the same thing here, except for every value along this function, it's the y value is going to change, right? It's not constant like it is here. So we can't come up with a specific number, but we can come up with a function, h of x, that would represent the height of any rectangle within this enclosed space. So what I do is I take, remember, all along here, these function values or y values are the maximum values. Okay, and when we take away the value of 2, which is the boundary from the horizontal line, that would give us the height if we calculated each and every one, which would be next to impossible because there's infinitely many points here. Okay, so our function comes from taking the upper function and subtracting the lower. So our upper function is negative, oh, that didn't come out very well, negative x squared plus 4x minus 1. That's my upper function, and I'm subtracting 2 away from that. So the height of any rectangle that's in a vertical direction between these two functions, the height for any rectangle would be negative x squared plus 4x minus 3. So I could plug in any value here between 1 and 3 and calculate that height. Okay, so go ahead and try 79 and 80. Pause the video. When you're done, come back and we'll compare solutions. All right, let's see how you did. So for 79, the upper function is this curve. Okay, the lower function is this line. Right? This one, when you look at it, the y values are always higher on this function than they are on this one. So we want to subtract in that order. So we're taking 4x minus x squared and subtracting 2x, which gives us negative x squared plus 2x. For number 80, this horizontal line is the upper function. So we're doing 2 minus the cube root of x. And that's it. There's nothing else we can do with that. Now, the book also gives you some problems where we look at the length where the boundary is in this direction. So now we want to take the function, or I'm sorry, it's not, well, I guess we could call it a function of y. This is the boundary that's furthest to the right, and the rectangle on the other end is bounded by the y-axis. Okay, so now to get the length of a rectangle bounded by these two, I'm going to take the 1/2 y squared and then subtract, this is the equation x equal to 0, right? So I'm really just subtracting 0, so it's just 1/2 y squared. For 83, now the vertical line is furthest to the right. We're looking at x values, so I want to take the largest x values and subtract the smaller ones. Everything along this curve would have a smaller x value. And again, x depends upon y. Just like over here, all of these are larger x values, and we subtracted 0, which was the other boundary. This time we're starting with the vertical line, which is further to the right than the curve. The vertical line is the line x equals 4, so it's 4 minus, here this x depends upon y squared, so it's 4 minus y squared. And that would give us the length of any rectangle going in the horizontal direction. Right? That would give us the length of any rectangle between these two boundaries. So that concludes the lessons for 1-4 and 1-5. I hope you have a good day, and I'll see you in class.